Does that work? Yes. So, maybe contrary to many of you online, my work is at the intersection of software engineering and AI. So I work on how to use AI to automate software development, and on the other hand, how to adapt software verification, software testing techniques for the assurance of AI-enabled systems. So I'm going to provide a different perspective, I guess, a software engineering perspective on the quality assurance and safety of deep learning models and systems, where I will show you an overview of how we have tried to adapt, in particular, software testing techniques and safety analysis techniques to deep learning systems. And so I will not present a single project, but rather an overview. And the reason is that very few of you online are probably interested in that particular aspect of applying software engineering to AI. So I just want to give you an overview of what has been happening over the last few years at an intuitive level, though it's not going to be a survey. So let me first give you an introduction, because again, you may not be very familiar with, for example, what software testing is. Software testing is basically the automated generation of test inputs in order to exercise a software system and effectively and efficiently detect faults, vulnerabilities, safety violations, whatever you're interested in. And of course, the question is that how can you devise efficient and effective test strategies? How can you make sure that your testing is sufficient in order to reach an acceptable level of confidence? There are different levels of testing. You can test components, you can do integration testing, you can do system testing. And another question is, what information do you have access to? Do you have access to source code or not? Are you driven by specifications? So it's a very vast field of research. And you also need a mechanism to detect failures automatically. Obviously, outputs cannot be analyzed manually. This doesn't scale. So this is often referred to as the test oracle problem or the test verdict problem. And you need mechanisms in order to help you identify the root cause of failures and then assess risks with respect to safety, security, and so on. So this is a 1 minute overview of what software testing is. And of course, nowadays, most systems, and especially the type of systems I've been working on, autonomous systems, for example, in the automotive domain or satellite domain, integrate AI components. And then the question is that, okay, then how do we, how does that impact testing and any other quality assurance practice? I mean, what do we do with that? When I talk about AI here, of course, it can be anything from traditional machine learning to deep learning, CNN, RNN, reinforcement learning, or generative models. But today, I'm going to focus on regular deep learning models, such as CNNs, for example, in the perception layers of autonomous systems. So I also do a lot of work on testing and safety of generative models, but this is another presentation. So the problem we have from a software engineering standpoint is that all techniques that are based on source code analysis, program analysis, are not really applicable when you have those AI components. And very often for those AI components, we don't have specifications. We may have some safety properties that we must comply with, but we don't have any form of specifications. The behavior is acquired through training, And the models we integrate are never perfect, no matter how much training we do. We know they're not perfect, especially over time when there is some form of data drift and, And of course, this has a significant impact on the quality assurance of such systems. And also, when we talk about quality assurance of, AI system, what are we talking about? I mean, trustworthiness. There are a lot of dimensions to trustworthiness. The robustness of system to input noise, for example, safety, security, bias and fairness for some systems. And there are many systems also where you need some form of transparency and explainability in order for the system to be deployable and to comply with standards. Today, I will focus mostly on uncertainty and safety and some aspect of explainability. And as I said, my talk will focus on, regular deep learning models, especially in the context of, autonomous systems and in particular the perception layer. So from a general test standpoint, when you do any form of verification, whether it's based on testing or anything else, ideally you would like absolute safety guarantees, especially in those critical systems. You would like whatever technique you use to be based on practical assumptions about the form of the input space and the architecture of the model, the properties being verified, and you would like the technique to be scalable because somehow it needs to be applicable with available resources for large models or even systems. And but the problem is that in practice, when you try to do it for real, because most of my research is with industry partners, you cannot have it all. I mean, you are dealing with very high dimensionality models, many parameters, and moreover, even many of the properties you're interested in are not model properties, they are system properties. Like safety is a system property, which makes things even more, difficult. So in the literature, you have two approaches, basically. You have people who try some form of formal analysis, such as technique based on reachability analysis, that are very often focused on robustness to perturbations, and that under very strong assumptions could provide guarantees about the models. And often also there are scalability issues with those techniques. And there is another approach, which is what I'm going to focus on today, which are based on testing, that is exercising the model, exercising the system in some way. And for example, techniques that are based on search algorithms, evolutionary computing, or other form of search-based algorithms. So of course, those are heuristics. They don't provide guarantees. But on the other hand, there are no restrictive assumptions and they tend to be more scalable. And anyway, in practice, when people are dealing with, the safety of systems, they rarely reach any form of guarantees. So that's a bit of an illusion most of the time. So there are testing, as a matter of fact, in practice, whether it's in the automotive domain, the satellite domain, or many other practical industrial domains, testing is still the main practical mechanism through which people gain trust in systems. And there are different types of testing. As I said, you can test, of course, an AI model in isolation, like a deep neural network, or you can do integration testing, system testing. And here you are looking for different types of faults and problems. And so today I will only show examples of testing deep neural networks and system testing. So at the model level, I'll start with a somewhat dated project, but that is simple. That is a good way to start addressing the subject. This was a project in the automotive domain where they had a camera installed within the car, and they were monitoring the face of the driver. and they were trying to predict the key points on the face of the driver, the corners of the eyes, the nose, the mouth. And this was used for different applications that I will mention later. And of course, testing such DNA model means that you want to try to identify as many images as possible where key points are poorly predicted within a given time budget or test budget. And then you want to be able to evaluate those testing results to somehow evaluate safety risks. So here we assume that we are in a context where we have a simulator in the loop to generate the images. And this is an important practical point. I'll get back to it. So example applications, for example, are drowsiness detection of the driver or gaze detection based on the interior camera. And therefore, when we are testing such a DNN, each key point is important, maybe important for safety. And each key point is a test objective. So in that particular case, we had 27 key points, so 27 test objectives that we could try to, for which we could try to find images that fail in terms of their, in terms of key point prediction. And so without getting into details, I'm just providing an overview. We used some algorithms from evolutionary computing called many objective search algorithms that are based on genetic algorithms combined with a simulator. And at a high level, you have an input generator, which is based on that search algorithm. You generate an input to the simulator that generates a test image. That test image is fed to the DNN that predicts key points. A fitness computation for each key point is computed based on the difference between the actual key points and the predicted one, and then fed back to the search algorithm. And then eventually, through a number of generations, we are trying to find in the space of possible images, images where critical test inputs are generated. That is, test inputs where there is a significant difference between there is a significant difference between the predicted test key point and the actual key point. And then, assuming we identify a high number of such critical test inputs, for example, in this case, we use regression tree in order to derive, as you can see here on the slide, to derive rules that, based on the simulator inputs, would predict whether or not we would have a low or high normalized error in the prediction of key points. So try to identify conditions under which the model fails in terms of key point prediction. And so, for example, here, the rules are based on characteristics of the face, the pitch, roll, and yaw of the head. And so, without getting into details, for example, we found rules where when the head was in a certain position, you had shadows on the face. And because you had shadows on the face, certain key points could not be accurately predicted. So this is very important because eventually such DNNs get integrated into a system, and the system is responsible to determine whether it can believe the predictions or not, or which predictions it can believe or not, and act accordingly. So in this case, if the system is able to know which key points predictions should be trusted and which one should not be, then it can decide which key points to use in order to predict the gaze of the driver or drowsiness, and which key points to ignore. Now, this was an example where you had images. You had a simulator in the loop. But there are many, many situations where we are dealing with a bank of real images, and we need a different approach. And we need to be able to select a bunch of images and label them for test purposes. So, and labeling, of course, is expensive in many situations. And so somehow we need a test strategy which is based on minimization. Select a minimal set of images that are labeled and used for testing. And we want basically a technique that allows a test engineer to have a fixed label and test budget and select an optimal set of images for that purpose. And the question is how to do that. So again, relying on evolutionary computing, we use a multi-objective search algorithm, but this time based on objective functions that are based on diversity and uncertainty scores. And I'm going to go a little bit more details. We need a black box approach because here, for example, this was part of a project with an automotive company, and they were basically testing the safety of DNNs, but they didn't have access to the training set or the internals of the models. I mean, they were using models from a third party. And the approach basically was based on trying to find first a set of test inputs that is as diverse as possible in the space of possible inputs. And of course, this is intuitive. The more diverse a set of inputs, the more likely we are to reveal faults. And we couldn't, as I said, use information about the internals of the DNN or the training set. And we needed some form of scalable and practical selection mechanism. So how did it work? First, for all the images that were being considered, we extracted features from those images, in that case, using VGG16. And you are probably familiar with that, so I won't go into the details. And then basically a test set, our test set was a matrix of features, where each row was basically a vector of features. And the way we measure diversity in geometric terms. That is, as you can see here on the slide, if two images are similar, the feature vectors are close to each other. And the hypervolume of the parallelepiped between those vectors is small. Whereas if images are very, very different in terms of feature vectors, we have a large hypervolume. So we found a computationally effective way of computing that hypervolume. And then the problem of selecting a set of images became a Pareto font optimization problem, where we try to determine using those search algorithms I've mentioned from evolutionary computing, in particular the well-known NSGA2 algorithm, trying to find the Pareto font in the space of Gini scores measuring the uncertainty of predictions and our geometric diversity score as computed on the previous slide. And then basically use images on that Pareto front in order to select an optimal subset for test purposes. Another problem.
A little question, Lionel.
Yeah.
Do you want to have questions during your talk, or you prefer to have them at the end?
I can have a certain number of questions during the talk, but if I get too many of them, then I'll have to adjust the talk in real time.
Because there's a very important, interesting question, I think, in the chat. Okay. I'll let
go ahead.
Ask them.
À Mathieu pour finaliser ma candidature.
Oh.
Sorry?
Thomas, are you there?
I'm here. I didn't want to disturb at this stage, but okay. It was just because you mentioned it was about the on the previous slides where you talked about the usage of found it very interesting how you
Which
try
one?
to derive rules.
Yes. Okay.
Yeah, when you try to derive rules to understand where
Yes.
in which condition the model behaves
Yes.
badly.
Yes.
And I was, because you mentioned then we need to ensure at system level that the right operations are planned to cope with when these conditions are met in real life. And I was wondering if it could also be used not for monitoring in real time, but for design purposes at system level. Just
Yes.
when you
Yes,
know that it behaves badly in this condition, then you try to adjust maybe, I don't know, the positioning of the camera, the choice of the camera to.
Yes, it's
Yeah.
exactly actually what I meant.
Okay.
That is, we know that those deep learning models are never perfect. We know that. So you have to have a mechanism to deal with uncertainty, so that even if the models are not perfect, the system is robust. For example, incorrect predictions you have to make sure incorrect predictions don't lead to safety violations. So yes, exactly. So you must, for example, you can have some form of guardrail mechanisms that is aware of those rules, and then decides which key point prediction should be used for guess detection and which one can be ignored. Because of course, for doing, for example, guess detection or drowsiness detection, you don't need the 27 key points. So
Yep.
the question is, which subset do you use?
But this information should also be given for the people who design the system.
Yes.
So they can adjust the design.
Yes, exactly. Yes, exactly.
It's very interesting.
Yes. But this is an example, but this is a general principle. In general,
that's how I took it.
It's a general principle that whatever AI model you use, it's not going to be perfect. Whatever AI models you use, you need to be able to test it to understand when it works and when it doesn't work, and then adjust your system architecture according to that. I mean, that's the only way in practice you can deal with this. Otherwise, the problem is that then those models will never be deployed because people won't trust them and they won't feel confident enough. At least, in the context of critical systems of some kind, mission critical, safety critical, Sorry, let me, I will probably not be able to cover my slides, but anyway, I'll it's better.
In that case, I propose to you that we leave a certain number of questions for the end so that you can advance in it.
Yeah, but that's okay. I don't have to cover everything. I will share my slides anyway if you're interested. And there are references at the end. So another problem that was posed to us by another industry partner is that, okay, they were not trying to generate automatically inputs. They had test suites, but they were saying, okay, how do we know that we can trust the test suite? How do we know we can trust the results? Because, of course, you can have a high accuracy because your test suite is incomplete. So, how do you know we can trust it? So, and this is a well-known problem in software testing, actually. It's called the test adequacy problem. And so we tried to devise a solution to do that. And I'll just jump to it without further. So what we did is that there were 3 phases in our solution. The first phase, what we did is that we took the model and we seeded faults into it. We call that mutation analysis in software engineering. So we, according to some strategy, we modify the weights, we modify the activation function, we seeded faults in them. So what we did is that we took the training set and where we know what are actual mispredictions in the training set, and we computed what we call the mutation scores. That is the extent to which the training set was able to detect those seeded mutations in the model. And what we did is that we then looked at the correlation between the full detection rate of a large number of subsets of the training set of different sizes and the mutation score of those subsets of the training set. And we basically built a prediction model to predict the full detection rate from the mutation score. And the relationship, of course, between the two is not at all linear for reasons I will explain. Mostly because, I can say it now, I guess, mutants can be detected, maybe harder to detect or easier to detect than actual faults. So the relationship is not linear. And then during the testing phase, what we do is that we seed mutants into the model under test. We calculate the mutation score of the test suite, and we predict with a certain confidence interval the full detection rate. And based on that prediction, then test engineers can decide whether or not the test suite is adequate. So without getting into details, providing just an overview, we obtain quite accurate results. And though the relationships were sometimes extremely nonlinear between the mutation score and the full detection rate, and that relationship varied a lot across models, which is not surprising. So another problem that was posed to us in terms of model testing, and again, here I'm providing with an overview. If you're interested in details, you can look at the papers. Is the fact that people had, for example, several DNNs that were trying to predict the same thing, but those DNNs, for example, were based on a different architecture, they were trained using a different training set, or well, you know, or one DNN was an update of the previous of the other one, you know, and there was a number of situations where you needed to use testing to reveal behavioral disagreements between the models. We call that we call the inputs triggering different behaviors, triggering inputs, and there were different types of applications. It could be used for selecting alternative models. You know, models that were more reliable or more accurate in more critical conditions, or understand the differences between an original and an updated model, you know, to make sure that the updated model was actually an improvement in critical conditions. And, or even better, as this actually was our practical case, people would have, you know, like it is often the case in safety tolerance systems, they would use several models and would decide at runtime which prediction to trust. That is, they would decide at runtime which model would be more trustable. So to do that, again, in software testing, it's a well-known problem. It's called differential testing. You know, you try to understand, to use testing to understand differences between several pieces of software. In our case, DNNs. So the approach at a high level is based on a trained generative adversarial network, and that is used to generate high quality images by learning to mimic the distribution of real images, as you know, for a domain of interest. And it's based on a generator neural network and a discriminator neural network, but probably, you know, most of you online know how GANs work. So we train a GAN for a given population, and in order to generate images. And we use a trained GAN to generate images that are fed to the alternative DNNs being tested. And we use two objective search algorithms to search the latent vector space of the GAN in order to generate triggering inputs, that is, generate inputs where the alternative models disagree, for example, in terms of classification, and at the same time generate images that are diverse as well. So that's why we use a two objective search algorithm. And the search manipulates the population of latent vectors. that are passed in input of the GAN. So the goal, again, to summarize, is to generate images that trigger differences of behavior between alternative models, and at the same time that are very diverse in the space of images. And so we, of course, evaluated it very rigorously on a number of GNNs, and we were able to determine that using the set of triggering inputs we had identified, we could train a very accurate machine learning model, such as a simple random forest model based on image features, to predict which GNN was more accurate when under which conditions. And therefore, that random forest prediction could be used at runtime to decide which GNN output to trust for a given input. I think I will skip that one. This is another project, I'm just telling you at a high level, again, where, in practice, in industry, people develop, deep neural networks that are then deployed in different contexts and tuned in different contexts. For example, that's the case in the automotive industry. Obviously, DNNs that are used on the road are used in different weather conditions, whether you live in Canada or New Mexico, or, And so people train generic models, and then they fine-tune them in different contexts based on different data distributions. But then every fine-tuned model has to be retested. You can't just trust the fine-tuned model, But you cannot test every fine-tuned model from scratch. It's too expensive. So you need a smart way of testing fine-tuned models that allow you to reduce the cost of testing. But I will skip the details of that one because it's too. Otherwise, I'm going to run late. Anyway, let me just go to. All right. Another thing, there is a very close connection between explainability and safety. Safety requires, as a prerequisite, that you understand when you can expect your DNN to be accurate and when it's not accurate, and so that you're able to determine whether it's acceptable, whether, for example, those conditions are rare or non-critical or vice versa, so that you can decide whether it's acceptable or you need some form of focused retraining. In practice, that's what you need to do. So you need to understand what those conditions are so that you can identify rare situations where it doesn't work and what mitigation mechanisms you need to use. And also in order, as I said, to guide retraining. So now let's imagine we need to do this, but we don't have a simulator in the loop like the first project I've presented. We just have a bunch of images that have failed. Where we had mispredictions, and we try to understand why, what are the conditions under which this happened. And of course, you might say, well, the engineer should just look at the images that fail and figure out what happened. Well, obviously, if you have hundreds and hundreds of images, like it's typically the case, that's not something that is particularly easy to do. So engineers need help. So we define an approach to exactly provide that help when we don't have a simulator in the loop. So we developed a technique called SAFE, which is black box. Again, doesn't require any internal information about the DNN, where during the first step, we extract features from imaging, again, for example, using VGG16, and perform dimensionality reduction, because, of course, there are many features in the feature space. Why? Because in the next step, we are using clustering, hence the need to perform dimensionality reduction. And we then perform a clustering based on the feature vectors of all those images to group similar images in the hope, and this is of course the intent. I mean, there are many details I'm browsing over, in the hope to group images that have similar root causes for mispredictions. Why? Because if we cluster images that have similar root causes, then people can, by analyzing only a few images, can identify the root causes leading to those predictions in each cluster with minimal effort. And actually, we tested this, as I will mention next. And then once also we have those clusters, we can, using smart sampling strategies, we can sample subsets of images for targeted retraining as well. So what we did is that we did actually experiments with engineers where we provided them with clusters and we asked them to, by analyzing randomly, 5 images from each cluster, to tell us what were the root causes of mispredictions. And we found out that actually people were, were pretty accurate in many situations. So that by analyzing only a few images per cluster among hundreds of images, they were able to understand the conditions under which, or that triggered those mispredictions, such as a driver wearing a mask, for example. So anyway, I was talking about model testing. Let me go a little bit through autonomous driving, system testing, with using as examples autonomous driving systems. You all know what they are. So the problem with ADAS testing is, how do we automate testing in a scalable and practical way, as you can imagine. The challenge is that there is an enormous scenario space, an open context, like many autonomous systems. Also, we have the test oracle problem. How do we detect automatically unacceptable behaviors? We cannot just rely on obvious misbehaviors, such as, blatant safety violations. We have no specifications, of course, for such systems, really, except the safety properties. And we have many such safety properties, unfortunately. And even if we have a simulator in the loop, simulation is very expensive. It's very expensive because it's physics-based. So it's, a type of simulation doesn't come for free. So basically, I've done several projects in that area, but I will only present one. Where we tried to do exactly that, try to come up with a scalable testing with a simulator in the loop for ADS. So our goal was to find a way to effectively search a scenario space, automate failure detection, even though we don't have real specifications. Or at least we don't have complete specifications. I mean, that doesn't exist for such autonomous systems, really. And we want to detect failures that are not just blatant safety violations, but also subtle undesirable behaviors, because it makes testing much more effective. So again, we used a form of evolutionary search, but something more complicated called cooperative co-evolutionary algorithm and metamorphic testing. I'll tell you in a minute what it is for those who are not from the testing field. So we use a combination of those two things. So what is metamorphic testing? It's an approach to testing where you look at differences in system behavior based on performing input transformations. So you transform an test input and you check whether the expected change in behavior happens. So for that, the goal of that is to address the automation of the test oracle or test verdict problem, which is very important in industry. So to do that, you need to define so-called metamorphic relations. That is where you explain how, when you modify an input, what should be the differences in the respective outputs. So you don't actually provide the exact outputs that you expect. It's really about relationships between input transformation and output differences. So for example, for a given driving scenario, if you add a pedestrian in the field of view of the car, the ego vehicle should slow down. So, you don't know exactly what should be the speed of the vehicle. You don't know, but you know that if you take a scenario and you add a pedestrian in the field of view, this is what should happen. So more generally, you change an input I to I prime, and it implies a predictable change in output. Otherwise, there is a failure. And, oops, sorry. This is a video. I hope it's not going to take too much time with an example of exactly what I said, if it doesn't take too much time to load. So here there is a driving scenario. It's a bit slow, sorry. And where the only difference, as you can see here, it's a bit small, is that there is a pedestrian. And somehow the DNA is confused by the fact that there is a truck in the background. And so it doesn't see the pedestrian and doesn't slow down. So that's the type of scenarios we want to find automatically. So we use also a coevolutionary algorithm. Again, I'm going to be intuitive here. It's a type of algorithms where instead of having one population that you evolve, you have two populations, and it allows for, in certain cases, more efficient search, and it allows for parallelism in the search. So in our case, we have two populations, a population of scenarios and a population of perturbations to the scenarios, where we add or delete objects in the field of view, we change the speed or trajectory of vehicles or pedestrians, and so on. And we manipulate those two populations, and they evolve in parallel. So that's a typical problem where you use those, coevolution algorithms. And so we assessed it, and what we did also with engineers is that we showed them the violation that we found. By in our case, the violations were violations of metamorphic relations, because that's what the search was looking for. The search was looking for scenario violating metamorphic relations. And we showed that to engineers, and we asked them whether they thought that those violations had safety implications or led to safety risks, and what was their severity. And we got feedback that confirmed what we expected or what we wanted to see, that indeed we had detected misbehavior that led to safety risks, critical safety risks. So to summarize what I've presented, I talked about testing and safety analysis and retraining of DNA models with or without simulation in the loop. In this presentation, I've focused on DNNs with images in input and performing classification, but of course you can generalize many of the things I've said. I talked about test adequacy. I talked about understanding the differences between DNA models in order to be able to combine them, for example, for more accurate predictions. I didn't talk about efficiently testing fine-tuned models. I talked about testing deep learning systems, in particular, safety-related properties, because anyway, safety is a system property in the end, not a model property. And I talked about safety analysis and decision through explanations. And I didn't talk about all aspects, all techniques that I used to achieve better scalability, but I talked about coevolutionary algorithms. I didn't talk about surrogate models. This is one of the slides I've skipped, where instead of using simulators, we build surrogate models for simulators to be able to use surrogate models instead of the simulators in a large percentage of cases in order to achieve better scalability. Things I've not addressed is a simulation issue, but simulation fidelity, inputs that are other than images, other properties than safety, generative models, which of course is what everybody has in mind these days. I'm doing also a lot of work on the testing and the safety of systems that include generative models, such as customer care software and stuff like that. There are also other related work I haven't covered, the testing analysis of reinforcement learning agents, how to automatically determine the safety boundaries of AI-based systems, the safety monitoring of any learned component, whether it's a DNN, or reinforcement learning agent or whatever. Differential testing of system updates is another important thing. And for that, I'll point you to references. Thank you.
Thank you very much, Lionel, for this very panoramic overview of a wide span of research. If I understand, this is essentially at least 5 years of different work. Yeah, it's amazing. So thank you very much for this incredible talk. There was a question back in, I think, rather at the middle of your talk, by that I don't quite recall exactly what was the particular paper you were presenting, but it
What
was
topic?
somewhere.
What was the topic? I can find the right slide if you tell me the topic.
Yeah. Laurent, could you be specific on it? We know that it was around the middle of your talk in any case.
Yes.
No, actually, the question was about the uncertainty quantification techniques you were using.
Uncertainty quantification. Yeah, the Gini
Because-
index.
Yeah. Okay. So for me, that's clear. But what about any regression task, or how do you do it in practice for any other regression task? Yeah.
Regression task. What do you mean by regression task?
Because
when you update a model,
no,
and you want to make sure,
no, not really. If I understood correctly, the Gini scores that you get is because you are doing a classification task, right?
Yeah, yes. This is an example with classification, yes.
You have a softmax, I guess, and you basically compute the Gini coefficient based on this vector at the output of your network. Am I correct?
Yes. For a given input, yes.
Yeah. My question is straightforward, I don't think there is such index for a regression task.
I see what you mean. Sorry. Yes. No, there are techniques for regression, but they are not as well known. But there are techniques for measuring uncertainty of regression predictions.
Yeah, and my question is, which one do you use in such cases?
Sorry.
No worries.
I don't have that in short memory. Sorry. It was a while ago. I forgot which one we used, but you can easily find them. I mean, I don't do research on that. Obviously, I use whatever I find in the state of the art, But I mean, any measure that works will do.
All right.
But
okay.
You are right. It's not as straightforward as for classification. Yes.
Okay. I was just curious if you had any tips or any advice for.
I can look at it, refresh my memory, and send you an email if you want.
No worries. Thank you.
Sorry for that.
No worries. Thank you.
Right. I have one question I would like to ask because in the very first, in the beginning of your talk, you talked about AI components, right?
Yes, because I was trying to be general, but in fact, all the examples I've shown were deep neural networks. But
exactly.
Yes.
So, but in any case, in the middle, at some point, you shifted to indeed systems.
Yes.
Where indeed I was at some point expecting to see metamorphic testing.
Yes.
Now, I have a question that maybe lies in between them in the following sense. So maybe instead of taking either just like a DNN as a model somehow in isolation, or to take the system itself, maybe there is a way of testing AI components in the sense that they are themselves pipelines of a central model, say doing the central classification task, for example, but also in where you have attached auxiliary modules, say uncertainty quantification model that is calibrated for this task, and maybe anomaly detection, for example, or OOD detection model that whose threshold depends also on the uncertainty quantities that you compute. So you have like some sort of interdependent pipeline of different models that are contextual. You cannot completely break them away, but they form an AI component, and on which you can also maybe test in the metamorphic sense its behavior, but in a more like a restrained way, that it is not like the overall system, for example, an autonomous car. And I wanted to know if it is something that you've reflected on and researched on.
Yes. Okay, let me start by giving you my perspective on the difference between model testing and system testing. The first difference is that when you test a model, you are testing its accuracy, more or less, or its robustness in terms of accuracy to noisy inputs or whatever, But you are testing its accuracy. So the type of property you are testing is relatively easy. I mean, it's not particularly subtle. It classifies correctly or it doesn't. In terms of regression, it predicts accurately enough or it doesn't. When you are testing a system, as you have seen here with metamorphic testing and the type of properties I'm talking about, first, the input space is much larger. You're testing, an input space of all possible scenarios on the road scenarios on the ADS with weather conditions, road topology, trajectories of pedestrian speed, and so on. And you're also testing for behavioral violations that are much more subtle. I've only shown an example where you had a pedestrian in the field of view, the car should slow down, but there are many, many other properties that are very, very subtle. You're not just testing for collision or like blatant safety violations. Okay, so that's why you have to define a number of metamorphic relations that capture those subtle properties, and the search and testing is basically guided by those metamorphic relations, and is trying to efficiently find input that violate them. And also, when you test at the system level, you're not testing whether the model is perfect or the model is accurate, because again, you can have monitoring component or guardrails that take care of the mispredictions of the model and do something to make sure the system is robust, or use several models, and as I've shown before, and trying to use the one that is expected to be the most accurate. So you are not testing whether models are accurate. You are testing whether the mechanisms you have in place to deal with the uncertainty of your models are effective, basically. It's because you are testing the system. So those, for me, are the differences between testing at the model level and at the system level.
Right, of course. And then there's in the middle, I guess, the operational design domain, right?
Yes,
that kind of gives you, I mean, if you take it from the point of view of a complex AI component, somehow an expanded version that is not as vast as the one that you have to take into account for the overall system, but that for an automated function gives you a span of scenarios that is also highly non-trivial to test. And so my question was on that very specific on the in between layer of complexity, if there is something that is well calibrated to to be able to test, to do testing at that level?
Yes, I'm not sure where you're getting at, but one of the projects I haven't. Sorry, someone just opened my door. One of the projects I haven't presented was when testing fine-tuned models, and here we use out of distribution scores to detect or to decide which input to test on the fine-tuned model in order to minimize the testing effort. And we look at the differential testing results in terms of output between the two models, but we also look at the Odin score of the output of the source model and the target model. By target model, we mean fine-tuned model, okay? The target model here is basically the source model that has been fine-tuned to a specific context. So we use that in order to try to predict what inputs in the new context, in your new data distribution, should be labeled for testing purposes and minimize the testing effort. So that's a context where we have used out of distribution scores for test selection.
Yeah, this is super interesting. I would wonder how does this, for example, can be used in tabular data, which is a complicated thing, right? More than images.
Yes, you're right. It's true that here, because I had to decide what to present, and also because I must say that many of my industry projects were in the context of the precision layer of autonomous projects, because this is where, in practice, deep neural networks have been used the most. So when you work in industry, that's what you tend to more frequently face as a practice, because people are still very reluctant to use this for control, for example. Because, you have the academic theory of AI and you have the practice of AI, and there is a big gap in between them. Yes, those techniques have to be adapted to different types of inputs, yes. But I think there are still general principles that can be used.
Yeah, absolutely. That's something very important to keep in mind. The somehow invariance of that you've presented in this panorama. I wanted to ask if are there questions among the room? We are essentially at the time. There is Bertrand that wants to ask a question. You can go.
Hello, yes, it's some kind of generic question. It's not related to your specific work, but it's a more generic question about safety of automated driving. In fact, a few years ago, there was a very good report it was called Safety First for Automated Driving, something like that, authored by a number of German manufacturers together with, I think, NVIDIA and a few others, maybe Google.
Yes.
And they came to a few conclusions. One of them is very obvious, but I think it's also very important. It won't be possible to guarantee 100% safety for self-driving.
No. But it's important to realize that when
just let me finish my question.
Sorry. Yes, go ahead. I'm sorry.
And so, in fact, and they said the conclusion that somehow an autonomous driving vehicle will have to release a number of constraints, whatever it means. It means violate some traffic rules or whatever. So do you think, generally speaking, that the society is ready to accept this lack of safety?
Well, no. Society, I mean, if you put the question like this, society is not ready to accept lack of safety in general. But I have several answers to your question. One is that when I talk about automatic driving system, I don't mean necessarily complete automatic driving system. I mean any system that helps automate certain tasks.
Starting at level 2 or 3, so level 3.
Or even simple example like I've mentioned before, like drowsiness detection of the driver.
Okay.
I mean, anything that helps, basically. So I don't mean necessarily complete autonomous driving, any automated task in the context of driving systems. And many tasks clearly bring safety advantages. I mean, now, if we talk about autonomous driving in general, yes, we will never be able to guarantee that it's 100% safe. But drivers are not 100% safe.
No, but we don't perceive human error as we perceive machine errors.
That's true. But in the end, if we want to be rational about it, the real question is whether it's safer than human drivers. That's a real question. And there are also other questions which are more legal. I mean, in the sense that when a driver makes a mistake and there is a collision, the driver is responsible, and the driver must be insured. When the ATRASS makes a mistake, then the question is who is responsible.
Yeah, complicated.
And then I think the problem is mostly legal. But anyway, when I talk about automated driving, I don't just mean complete automated driving.
Okay.
I mean any automated task helping the driver.
I think that in fact most of the safety will be acquired by a combination of machine and humans.
Yes, I agree. Yes.
Okay. Thank you.
But of course, from a research standpoint, ADS are very interesting case studies because they are very complicated, and the context is very complicated. Of course, there are other contexts where autonomous systems don't have to deal with such a complicated context.
Yeah.
Thank you very much.
Yes.
Thank you. There's a final question from Peter Chu. Do you want to ask it or?
Yeah, sure. Thank you very much. From the customer perspective, testing activities incur cost. How do you convince the customer that new testing methodology, for example, can offer greater confidence or safety?
Well, you have to experiment with some of their case studies. Is what we did. For example, I worked with General Motors, and we tested some of our techniques with a lane merging system that they developed. And no, you have to apply the scientific method. You have to have rigorous experiments and rigorous evaluations, and ensure that you can detect problems quicker, better. I mean, there is no other way. You're not going to convince them with hand waving, that's for sure.
I think we didn't quite. I think that Peter was saying things, but I think he got bad signal.
What? Sorry.
I think that Peter, if you made an answer, I think that we didn't quite catch it.
Martin, can you repeat it? I missed the last sentence of your question.
Oh, I was just saying that I think you answered you replied to Lionel's answer, but that we didn't quite catch it because of connection problems.
Do you need me to? Probably I misunderstood you. Do you need me to repeat the question or?
No. I think you just agree. I mean, you made a quick reply at the end, but we didn't quite catch it. I was just making sure that we didn't miss anything important. Okay, great.
Yeah, because during the no problem.
Okay, great. So
during the bid proposal. Often the customer complains about the high cost of test activity. Yes. So we reduce our test success criteria. And for instance, if you introduce a new test methodology, it needs to be a proof of concept. And a lot of things, new things, cost a lot of things.
And also it needs to be fully automated so that the cost is a computing cost, not a people cost. That's the point of many of the things I've presented. It was about reducing the manual cost or the engineer's cost, or even removing it entirely, if possible.
Yeah. Well, thank you very much, Lionel, for this great talk.